Hello, and welcome to this edition of Mirabilis Design's webinar series on technology innovation. I'm your host, Deepak Shankar, and today I'm going to walk you through the very enhancements of interconnects that have finally led up to network on chip. Now, today, in addition to network on chips and interconnects, I'm also going to talk about the role of multi-die interconnects such as UCIe have transformed the overall network on chip solutions, the requirements and the requirements. The title today is Designing the Interconnect is Not for the Weak-Hearted, and that is absolutely the truth. As you will see, the growing complexity has made it almost impossible for a single person to design the entire interconnect. There are so many moving parts and so many different variations that without fully understanding every device connected to the net, without fully understanding the workload, it's almost next to impossible to design your true SoC architecture. Today's agenda is fairly simple. We're going to start off with focusing on the challenges. We're going to move to the methodologies. We're going to look at some experiments. And then we're going to look at how VisualSim helps you solve this problem. To get started, let me just introduce system level exploration or system level analysis. This is all about design. It's not about validation. It's about taking a paper architecture and converting it into something that's fully validated, something that's fully optimized, fully tested before you go off and implement. It's not the process where you purchase some IPs from certain vendors and try to build everything around it. It's about selecting that vendor first before you go off and try to do the actual development. So in today's market, let's pick up something that's very well understood. You have multiple compute resources connected through a NOC at the top level, and then you could have it replaced eventually or have it separated out with a multi-die solution as well. Where do you start off with? You can start off with a very basic. How fast should the clock speed? Whether I need a tensor inside my GPU, whether I go with a Neobus or process in memory or with a RISC-V or with a Tensilica core. The most important thing that comes out of this thing is really about understanding the behavior. What is your application? How do you map your application to all the different resources within your system? The challenge comes up is that every resource has certain benefits, but every resource also comes with a price. Could be a power price, could be a memory access price, could be a bandwidth price. So really understanding how the different mappings, how the different behaviors interact with your system really ensures that you're going to get a highly optimized and fully validated product. When you look at your architecture, some of the key things when it comes to the interconnect are how many ports do you need? How many modules? What's your interface buffer? What's the quality of service? What's the interconnect speed? What's your optimal mesh size? That's how many X by Y do you need? Being able to first answer all these questions become the primary motivation. And that's where today's webinar is focused on, which is on the network on chip. Now, all of these have one major constraint, which is power. You really end up with having to take a look at power before you try to optimize this. Fully understand where your power is being consumed, where's your peak, where's your average. Now, once you've fully understood this, then the next thing is, looking at setting up your experiment space. What is it that you want to do? Here, first and foremost is selecting your interconnect. What type of interconnect? Do you want a shared bus, AXI type switch? Do you want a network on chip? Do you want a crossbar? Do you want a mesh? What do you really want? So once you have that in place, then you say, okay, what do I want for each level of hierarchy? So domains are a hierarchy. The backplane is a hierarchy. So again, you come back to the same question. And this becomes a little more complicated when you also add the multi-die, because each individual die can have its own topology as well. Then comes up the next question. Can the commercial products that are in the market help you solve your problem, or do you need to customize it? Do you need something fully built up from scratch? And there are benefits to that as well. Then comes something that can be a game changer, which can really topple your architecture, which is coherency. And how do you set up coherency to maximize your cache hit ratio? Then, of course, the monolithic versus multi-die, for which a lot of articles have been written, and we'll also be talking about it. And as I said about it in the previous slide, power management. Is your power management really giving you benefit? Is it bringing down your peak power? Is it bringing down your total power? How do you measure that? Then looking at more intricate parts, do you want a flat or a hierarchical topology? What is your criteria? Is it really about maximizing memory bandwidth? And finally, how do you put it all together in relationship to the SoC generation methodology that you have, the configuration tools that you might be using? How do all of these flow between those tools and your system level modeling environment? How does it ensure that you make it as seamless as possible, or more importantly, accurate as possible? Now, when I look at the coverage experiment, we typically start off with a block diagram. The block diagram has to have sufficient information to help you get going, meaning that you can create a model using IP libraries. From there, you start defining what your constraints, what's your requirement, how much of the SSL cache buffer occupancy can I afford? How much can my XP router buffer overflow happen or not happen? What should be my task latency? What should be my hit ratios? Being able to ask all of those questions and set up what you want as your requirements. And at the same time, set up what are the things you want to modify for each. You want to modify just your cache sizes, modify the number of cores, modify the, how many levels of caches you have, modify how many DMA lanes you have, being able to look at all of those. Once you set up everything for your model, then you want to run a regression. Now, remember, your regressions are tied to your parameters, but they're also tied to your requirements. So you want to set up these requirements in such a way that you run different sweeps and see how they respond to those requirements. Are these requirements passing or failing? Now, when you run these, you get a variety of plots. They can be looking at the requirement, they can be power, they can be latency, they can be quality of service, they can be performance, they can be any of those kind of attributes. Now, before we get very deep in, let's take a look, do a case study. Let's look at a data center SoC. In this case, the data center SoC for neural network application can handle up to 30 million vertices, less than 40 watts of power. And we want to run something like a ResNet workload, which has to complete the inference in about 3.2 seconds. Now, what are the challenges here? Obviously, buffer overflow is something we want to prevent at the interconnect. We have some memory throughput thresholds we have to achieve. We've got to see how many cores do you really need to meet the 33 millisecond response time for each frame. And lastly, what kind of power management technology should I use that will actually get me benefit for these types of applications? Now, let's start with a block diagram of this kind. Now, we have to pick and choose from the VisualSim library, and we pick and choose these different components from the processor library, from the NOC library, and so on. Now, notice over here, we have picked a very specific processor for which there aren't any commercial cycle accurate or microarchitecture models. And one of the things that we as in Mirabilis Design and VisualSim provides is a large library of processor models plus a large IP builder family as well. So if you don't have the processor model, it's something that can be built in about 2 to 3 days. More on that later. Also, how do you create the workloads, both synthetic and leveraging existing workloads? And finally, using the performance and power reports that are generated from VisualSim. So once you got all of this, you assembled up your model, you want to run regressions. You want to try different experiments. Once you put these experiments in place, you get different types of reports. Again, can be power, performance, area, functionality, any of these kind of attributes. And then you can establish constraints. These evaluations of these constraints are centered around while the simulation's running, there's an AI tracker in the background that's constantly looking at the model results and seeing if any of those items are failing. So if they're failing, it demonstrates that that combination of metrics or combination of parameters do not meet your metrics or do not meet your requirements. So you need to go try something else. So here's a VisualSim block diagram that's the equivalent of this paper block diagram. And what you get finally after you do all of your analysis and your experiments is you get component lists, clock speeds, buffer sizes, schedulers, algorithms, all of those fully defined with constraints on your performance, correctness, and power, so it can be handed off to your implementation team to say, hey, this is what the requirements are. This is what is our block diagram. These the details are here. We can go build this. Also, the same model can be, or a variation of the same model can be handed off to the implementation teams of the vendor from the customer environment, like say an OEM, that can then go off and build the overall finished products. So it's not just for internal use within the company, but also for use by your end customers. Now, what is the VisualSim solution that enables all of this? The product really takes in a concept. There's an underlying simulation engine which contains a discrete event simulator similar to Verilog or System C or any of those kind of tools. Has a large library of 500 plus components. These are the components that allow you to very quickly assemble up your particular system. Now, there are some other features. The key features is fully graphical, so you're not spending a lot of time debugging C++ compiler issues. You're spending more time debugging your architecture. Now, as you keep running these simulations, you may also find that, oh, I have existing IPs, or I have IPs from third-party vendors, or I have code that has been written in the past. And there's a whole API environment that allows you to integrate all of those into the same environment. And finally, there's a regression tool that allows you to run a variety of trade-offs and a variety of experiments to finally get an executable specification. Now, how does the Mirabilis Design work? We can provide you VisualSim plus libraries, plus training, plus we can also provide you modeling services. Now, what are these system-level IP libraries? These system-level IP libraries is a large collection of all the elements that are required to assemble your model and components that are required for you to be able to build your own custom building blocks. So it's IP builders and IP libraries as well. The nice thing is these can be at the IP level, semiconductor, or at the full system level. So the idea is that not only do you test it at your chip level, but you can also test it in the context of an application. Now, how does the solution work? So you can build a model that either uses pre-existing or reusable IP blocks that have a set of parameters that allow you to customize it to be able to indicate as being from a particular vendor or a particular implementation. There are a set of either debugging tools or there are a set of statistics that automatically get generated from the model. At the same time, you can define your own hierarchies, and they can be multi-level hierarchies. You can also use the custom IP builder, in this case for AI engines, that can then go on to build up a very large system. And then there are utilities like power and thermal and a variety of other components as well. These are the basic building blocks that are required for you to be able to assemble up your entire SoC within VisualSim. Now, before we get into details of looking at a specific use case, it would be good to try to understand NOC modeling. Network on chip modeling really involves 3 levels of abstraction. Abstractions are different levels of modeling that contain different types of information, and conducts different types of analysis. Highest level is really stochastic or queuing theory models. These focus on the overlap of latency and throughput without a specific implementation. Doesn't talk about a 7 nanometer, doesn't talk about using an ARM processor, doesn't talk about using an Ethernet switch from a particular vendor. Rather, it gives you an overall picture of what is happening in your system. From there, you transition to selecting a specific vendor product. We're looking at the timing, looking at the microarchitecture of, say, the processor, cache, memory, DMA, IOs, and the interfaces to allow you to put the entire SoC together. But at this time, it becomes fully cycle accurate, not pipeline, but fully cycle accurate, and be able to carry as much of the information in the model as possible. And finally, you have a microarchitecture. Microarchitecture plays a key role when you're trying to actually implement a particular component as opposed to trying to reuse a third-party vendor product. This becomes very important because not 100% of your chip is going to be a third-party vendor. Some of them are going to be part of your custom design. And also, you might use this operation to be able to fine-tune your vendor specification by modifying some of the constraints or some of the attributes that are associated with it. So microarchitecture plays a dual role there. So this is how a stochastic model looks like. So you have a block diagram, which is really a flow diagram with the algorithms. You assemble them up as a set of queues and schedulers and resources. Then you move over to a hybrid NOC modeling, which is vendor specific, like say an Arteris NOC in this case. So you have everything from your NIUs on your master and slave side, your quality of service, your limiters, your buffer sizes, the clock speeds across each of the ports and across domains, or wiring, wire delays between the subsystems or different routers, and of course the most important thing, the routing table. So you assemble up these when you start moving more into the hybrid. And the purpose for doing that is now I need to see the throughput, I need to see the buffer occupancy, I need to see the quality based on the QoS that I'm providing, how much of the memory bandwidth I'm getting out of the whole system. And lastly, you want to look at the microarchitecture of your model. So if you take the same Arteris NOC, you now break it down into a master flow control with an initiator NIU, mux buffer, demux with a target NIU. So you can connect them up, and notice here we have one path going in one direction, the other path going in the other direction. So you're breaking it down into a very finite set of components that are mimicking the extreme detail of each of the building blocks or each of the individual components. Now, a lot of things can be done over here. For example, if you look at the tracing, just for one movement of a round trip from the source requester going to the memory and coming back, you can see how many different individual blocks that it's hitting. Similarly, the debugging, you can see all the debugging details of what is happening in every block. In this case, the master flow control block is the one we're interested. We added out, and you can see what is happening through this particular component. And finally, you can generate all the different types of statistics that are required for your particular system. In this case, the NIU was our primary interest, the initiator, and the target. So you can see what the statistics look like in those. So now that you've seen it, you see 3 levels of modeling. Now we're looking at how do we start working with the vendor tools. So like Socrates is a popular tool from ARM. And you can see here, this is the block diagram in Socrates, and these are all the different configuration files. Using this in a day or so, even with this kind of a simple model, I know, but even a complex model within a week or so, you can assemble something that looks like this. So you're importing the configuration files, assembling them up, and you'll notice they mimic exactly the block diagram that was inside of the Socrates too, with all the different configuration components. So you're essentially recreating what is in Socrates, but the difference is now you're going to start plugging in your processors, start plugging in your IP blocks, start plugging in all the other components so that you can create a true SoC and run that entire system simulation. and also generate a variety of statistics, can be at the cache level, hit miss ratio, to the PCIe switch, receiver and transmitter megabytes per second, to looking at the CMN Cypress and looking at what the mean latency is, to looking at the ACE bus and seeing what the activity is on the ACE bus. And of course, getting graphical output, looking at the throughput as well. Now that we've seen how the system behaves, we're now looking at an overall system, a large monolithic system that we have broken it down into multi-die, and we're really focusing on the network on chip associated with it. So if you take this was our original block diagram, and you can see we've broken it down into 3 dies, 1, 2, and 3. This one has 2 SLCs, this one has 2 SLCs, and they each have 2 DDR5 memories. And in the middle, you have the actual 65 tile core, and they're connected through 4 UCIes to the other dies. Now, for something like this, the key aspect is we're going to, as we said, we're focusing on the network on chip. So what we're looking at is what are the varieties of experiments. So some of the experiments are focusing on the cores themselves. So, what happens if I change the number of cores? What happens if the addresses that are going are sequential versus random? Varying the buffer size on the NOC, changing the thresholds, and then looking at what's the latency and the associated power consumption. If you notice in this particular case, except for the first one, everything else pretty much consumes the same amount of power. And what you notice over here is that the first one does consume substantially more power, because we're looking at almost a 30% higher power than the rest of the system. Of course, the mean latency is much lower. The DRAM bandwidth is also much higher. Though the interesting thing is there's item number 3 here, you'll notice, has only about a 35 or 40% drop in your latency, but your system level cache is about the same throughput as item number 1. So there is some opportunity to be able to optimize the system. The interesting thing you'll notice is that the UCIe bandwidth on the maximum side is about the same for all of these. Now, when you start looking at just the RNF, which is we're looking at the end-to-end latency within the network, you will notice that we can also generate individual latencies for each of the different starting and ending points, as you can see over here, for different traffic rates and different configurations, just like what we did earlier on, looking at the different attributes of all the different components that are within your particular design. Now, when you look at the latency requests per cluster, in this case, we're interested in cluster 1, except for experiment 5, where we looked at cluster 6, is that you can see the latency is actually different for each one of them. Many reasons, even though they're all 8 cores, there can be address differences, there can be the memory bandwidth differences because of the RNF's buffer sizing or the clock speed of different components. You can get all of those kind of things, and that shows you a big variation in the latencies. The one that's most interesting is really the experiment 3 on the bottom left, because here what you're seeing is that the latency is actually increasing. Now, if you notice cluster 1, it starts to flatten out towards the end of this simulation, but the cluster 1 in the experiment 3 is slowly increasing. Now, experiment 5 is interesting because not only is it increasing, but it's increasing very rapidly in a linear fashion, which indicates that that's not a solution that's pretty acceptable. Now, experiment 4, you can say to a certain extent is acceptable, except for the fact that once in a while you're having these spikes, but otherwise it's in a fairly good range. Now, one of the things you should notice is that experiment 1 is a substantially lower latency than all of the others, similar to the experiments 5, which is actually even lower than the experiment 1 in terms of latency. Now, let's take a look at the 64-tile cluster. In the 64-tile cluster, we have 8 clusters, and each one of them has 8 cores, and they're all connected to their caches using AXI buses. Now, again, you can notice we have 3 or 4 levels here. We have the XPs, we have the AXI, and the router here. At the top level, we have the UCIes, and then we have the XPs. We're connected to memories. So you can actually have multi-levels of interconnects in one single model. Now, here what you can see is you can see the two dies. So the die 2 and die 3, which is the dies on either side, are identical. Die 1, which is the middle one, is the one that has all the clusters, and it has the complex NOC that connects all the clusters and the UCIes together. Now, one of the key things of modeling, especially system level modeling, is to ensure that you're not just capturing a model for one purpose, like a high level model for one purpose, a microarchitecture model for another purpose, a power model for a third purpose. Rather, a single model should capture everything, which is what we do here. In this case, you can see the database that captures the information for the middle die. In this case, we are capturing the information for the ARM cores, for the AXI buses, and for the routers, the NIUs. For all of those, we're capturing the power in this, and we're running the simulations for that. Now you can see how the power changes. If you remember how the plot was earlier for the latency, you can see the power is actually quite similar here for the power related to the latency as well. And one of the things you notice is experiment 2 is the one that's got the highest power, but the one that's most interesting is actually experiment 4, where the power is much lower than all the others, but we have the spikes more often, and they're actually almost at like 30-40% over the average. So which means that your cooling cost has to be significantly higher to handle just those spike points. And it's very important that you actually provide that information early to your thermal designers, because this will have a huge impact on the cost as well. So if you look at it, the exploration of an SoC is not just about the power or the performance or the functionality. It also all leads to cost and delivery and the resource required and the implementation schedule. One of the things that's key here is that when you're doing these system level verifications, you're not just testing an IP, you're not just testing an SoC, you're testing all of this in the context of the application. Could be a data center, could be automotive, could be an industrial system, medical, but it's really testing it, how it's going to behave in the final application. So when you look at a final application, what you're really looking at is a system. So in this case, I have a car. It's got gateways, it's got buses, it's got switches. It also has sensors, it has ECUs, and also high performance devices. So if you look at this whole thing, I have some CAN buses, TSN buses, I have gateways. So I have a variety of things that are connected up into this network. Now, I'm going to take this and I'm saying, okay, this particular system is really important for my advanced braking operation, or this particular SoC that I'm doing. It's a 10 silica based SoC, and I'm interested in seeing how it behaves in the context of this particular application. So when I look at it, there are so many different things that happen inside of your braking ECU. There's diagnostics going on, there's like speed calculators, there is other algorithms that are trying to determine, when and how much the braking should be. And what you have is other kinds of resources or other kinds of elements that impact your system, like reduced amount of power availability, which leads to a lower clock speed. Or it can be that there is some errors on your network, or there are some schedule tables that have been misaligned in your memory database. How do they all impact your system? So when you look at it, what you're going to see here is the latency, if you notice, is within a very small range. It's between about 2.2 and 2.5. So it's like less than 10% impact on your system. But what you notice is the sudden spike in the initial power, and then after that it drops off. But the worst is your break latency. Notice it's constantly increasing. So which means at some point, you're going to start off where you were braking within about 400 feet at 60 miles an hour to it's suddenly becoming 1200 feet. So even though the processing latency is the same, the DMA is the same, power's kind of leveling off to the smaller number for this particular task, but your break latency is a problem. So you have to look at, is it on the network or is it on the SoC? So this can be used by the OEM, but it can also be used by the SoC team to really understand how their product fits in the context of a particular application. And this becomes a very important aspect of system design or system exploration. How does this product behave when you put it into the real application or into the real OEM's final product? Now, as I was talking about it, one of the things that we talked about is power modeling. We talked about how we have a database, and while the system is running, the power is continuously being calculated and captured. It's not something where you're running an RTL and you're like capturing all the events and then associating delays with the events or associating some power number with the events, or you have some tags inside or registers inside of your chip, and you're running a video event and you're looking at how how much of power is being consumed every time, and you take a percentage of each state that the device is located. Rather, while you're running the simulation, you're actually capturing what is happening in the system and how that's impacting power. So it can be transients, it can be power management, it can be the actual workload, it can be waiting for data to come back from memory, it can be any combination of these things. So if you look at it, you have to look at the end-to-end power. So it's like you might have, if you take a car, you have the power generator, the electric motor, you might have the battery subsystem, then of course the power consumption. And remember here, the power is not just your electronics, your electrical, your mechanical systems as well. And of course the power management and what kind of a role it plays, especially relative to temperature and heat and other aspects as well. Now, one of the key things for an SoC designer is the power system in VisualSim does not just tell you what your power consumption is. It also generates things like UPF files, system Verilog files, the VCD test benches, so that you can also use that either to verify your downstream, but also use to test the implementation of this power management system. And of course, there are other attributes that are generated that can also be used to size the voltage lines and what is the maximum voltage you need on each of the lines. So the attenuation, for example, still produces the same voltage or the required voltage to get the required clock speed at all the way at the end of that particular line. So with power integration, as you can see, you have a model, you provide the database with the power table, you have all the different statistics and power and performance related, you have the timing diagram, and of course, you have the system Verilog output that is used for your system level power testing. Now, one of the things I was talking about earlier is our regression run, which is where the AI-based simulation comes into play. So while the simulation is running, the metrics are constantly being evaluated to see if any of them fail. So if any of them fail, it's immediately noted to say these failed, and this was the cause of the failure. And so you have the ability to go and make those modifications, rerun it, and see if that resolves the issues. Finally, system verification. Now, system verification is not just about connecting a top-level system model to RTL, but rather it's about what is the kind of data you need from the system model that can be reusable either for your C code or it can be reused for your emulator or your Verilog code. So here the focus is primarily on performance and power verification. So you can reuse your golden test benches because you're running a large number of these test cases. You can also reuse parts of the IP that are not yet available, but are available in the system model, being able to reuse them for testing maybe a subsystem in the underlying implementation. And of course, you want to link it eventually to your emulators or to your FPGA boards or even to your C code that you might actually be implementing on your physical hardware. Now, when I look at VisualSim, this is the VisualSim modeling environment. And you can see there's the libraries on the left-hand side, anything from process generators to resources to traffic to a variety of interfaces and interconnects to allow you to assemble up these models. So some of these models could be using off-the-shelf components, like in this case, like a PCIe 6 is a component to the library, or a UCIe, which is another component to the library. So if you modify any of these, they start behaving like a particular vendor implementation. Similarly, you can see each one of these building blocks has a unique set of parameters that you can utilize to fine-tune the behavior of that particular component. Now, once you're done with that, you can also look at the performance aspect. So it gives you, standard stats like latencies, buffer occupancy, the throughput, what is the average throughput, gives you statistics on each one of the individual components. Like in this case, it's what is the ACE bus doing. It'll also give you other things like, for example, for the, CMN or for the routers and for the switches, what is your latencies, what's the buffer occupancy, gives you what's happening within your UCIe, where's most of the data coming from, which port has the maximum latency. It provides all of those kind of statistics or information, and also starts providing you information related, like in this case, the PCIe switch, the cache controller, the memory, gives you all of that data as well, so that you can very quickly make decisions as to what exactly your particular system is doing or how exactly I need to modify my particular system. And every one of these components that you see in the model can be easily modified. So for example, I can go in, say, into the PCIe, I can open block of the PCIe, and you can actually see all the underlying code and the underlying structure, which is within each of the building blocks. So without having to come back to Mirabilis Design, because you can always come to us for help, having come back to Mirabilis Design, you can go and modify any of these things to create your own implementation. Also notice these are what we call our IP builder blocks. So we're not just building the PCIe from scratch, but rather we build building blocks that can be easily reused for creating other blocks. For example, the building blocks here were reused to create CXL, create PCIe, create UCIe, all of those. We're using a single set of building blocks that was slightly modified or parameter changed to make that implementation. So to finally wrap up, this is all about creating better products. You have one product, you need one model. You don't need half a dozen models. One model to study the whole system. And to be able to have one model study the whole system, you need a large library of IP components and IP builders for every part of your subsystem that you're going to be building. Also, you want to tie in your requirements very early in the design process with your analysis so that when you run your regression, you can figure out which are the variations that meet your requirement. Modeling using system level design at this level has been shown to eliminate almost 90% of the bottlenecks prior to your development. And this is demonstrated over a 40% schedule savings. So fully documented by our customers. There's a lot of articles on the web that provide this data as well. With this, I'd like to thank you for attending this webinar. I hope this was useful. Now I'm going to open this up to questions. Feel free to ask any questions and we'll be able to answer these right away.